So I want to know what effect it has on our idea of domination if I switch from closed neighborhoods to open neighborhoods. A vertex no longer dominates itself. It only dominates its open neighborhood. Well, if I do this, then I'm going to have to change my idea of a total domination set, right? We had a dominating set. Now I want a total domination set. So let me go back to the definition from last week. A set was a dominating set if and covered in this case included being a member of the set or being adjacent. How does that change here? Which means that every vertex has to be adjacent to something in S, not including S itself, right? Not including the vertex itself. So if I have a vertex, I've covered everything around it. Still haven't covered it until I include one of the vertices from that neighborhood. Now you might be adjacent to more than one, but you need to be adjacent to at least one vertex in the set S. But that means a member of S isn't adjacent necessarily. That was the difference. In a dominating set, the vertices were not adjacent to each other, were they? Not necessarily. So what is guaranteed to F up a total domination set, a total dominating set? There's a guaranteed way you can break this. As a matter of fact, any isolated vertex, right? Because then the neighborhood is empty. But we can't cover it. Because I can't cover it using itself. I mean, think about it. Any isolated vertex is stuck being unable to be covered. Because I'm only allowed to cover the open neighborhood. I can't cover it with itself. And there's nothing connected to it. If I have no isolated vertices, at the very least, I could use all of the vertices, because then everything would be adjacent to something else in the set. So I know I have one. The question is, can I make the smallest possible? So I'll have a dominating number. Now I'll have a total dominating number, total domination number. And such a set will be a total dominating set. And if I can find one, that's a minimum. V's on this side. This is the same graph we used on Friday. We had both a dominating set and a minimum dominating set for this last time. What was the minimum dominating set for this? Say again? UVW. Because U dominates U1 and V1 and U. V dominates U1, V1, U3 and V3, and V. W takes care of U2, V2, U4, V4, and W itself. But from a total domination perspective, if I use that same set, I've missed U, V, and W. All right, wait a minute. If I pick any vertex in this graph as part of a total domination set, I must pick one of its neighbors in that same total domination set. If I pick V, I have to pick U1, V1, U3, or V3. Otherwise, I won't ever cover V, because the vertex no longer covers itself. So if I pick V, I have to pick one of those four to cover V. If I pick W, I must make sure I can cover W. So let's start with those two. Let's start with V and W. Okay, $64,000 question. Why did I pick those two to start with? They have the highest degree in this graph. I cover the most other things with them. Great, wonderful, perfect routine. So, if I pick V, taking care of those four. But notice V and one of those would cover 5. W and one of those would cover 5. There are 11 vertices here. I have to pick something that covers the missing vertex. What vertex is missing from my list? There's no U anywhere in that list, which means one of my choices needs to be U1 or V1 to make sure I can get to U. And the important note here is that the 5 that are covered by V and a neighbor are disjoint, distinct from the 5 covered by W and a neighbor. But I need to ensure that somehow I cover U. And it turns out that if I do that, I'll do V and a neighbor. I can use either U1 or V1 to ensure that I cover U up there at the top. Somebody flip a coin, tell me which one we're using. Say again? V1. Then W covers all 4 of these, and I can pick any of those neighbors, cover W. I think in my notes, I wrote down V2. Now, that tells me that I can do this in 4 or less, right? My total domination number is less than or equal to 4. Why must it be equal to 4? Why can't I do this in 3? And that would leave me at 9. I got to get to 11 somehow. Even if I use the biggest possible degrees, the neighborhood of V and the neighborhood of W are disjoint from one another as sets. They're adjacent, but they're disjoint. W's neighborhood, V's neighborhood. So I have to have one from each of those neighborhoods to cover V and W respectively. I can't do it in 3. And that means that the total domination number of this particular graph is equal to 4. Questions? Some of you are looking at my handwriting. I don't know if it's my handwriting that's the issue or if it's for the statement that I've written down is the issue. This really is establishable by cases. So let's go think about a cycle. Cycle of length n is a true regular graph. You pick any vertex, it's got a neighborhood of size 2. But the vertex doesn't cover itself. So I, as a vertex, cover the person to my right and the person to my left. But in order to cover me, you need one of them. Pick one. That means that the person on the other side of the person to my right is also covered, aren't they? So by picking a pair of adjacent vertices, you've covered a group of 4. So now it depends on how many I have left over when I divide by 4. If I divide by 4 evenly, claim it's n plus 2 over 2. If I have any other remainder, if I divide by 2 evenly, claim it's ceiling n over 2. If I have a remainder of 1, same thing. Remainder of 3, same thing. Remainder of 2, something different? What the? Well, these 3 cases are all actually pretty easy. So let's count this out. As I just said, any 2 adjacent vertices gives you a covering of 4. I want to think of the edges as adding mod n, but I'm going to use 1 and n instead of 0 and n minus 1. This one's tight. So case 1, I'm congruent to 0 mod 4. I have 4 with none left over. Well, then I can pick 1 and 2, skip 3, skip 4, pick 5 and 6. Why? Because 5 covers 4. Notice what I didn't pick. is Vn minus 1. Because V1 covers Vn. Vn minus 2 covers Vn minus 1. So I pick 2, skip 2, pick 2, skip 2, pick 2, skip 2. And each set of 2 covers the one before it and the one behind it. That's exactly half, right? But 4k is evenly divisible by 2. So ceiling of n over 2 is n over 2. Ceiling of an integer is an integer. By the way, a cycle gets decomposed into 2 one-factors, right? Take every other edge. You have a one-factor. Even edges or the odd edges, your pick. This set is exactly one of those 2 one-factor set of endpoints. All right, what if I have 1 left over? There's my cycle. Vertex 1 to 2 to 3 to 4, 4k minus 3, 4k minus 2, 4k minus 1, 4k plus 1. I'm back on. Well, what is this set going to miss? What am I going to fail to cover? That's the same exact set as what's up there. That's right. V1 covers V4k plus 1. 4k minus 3, 4k minus 2 covers 4k. This one, V4k, got missed, didn't it? Everything else got covered the same way it did up there. V3 is covered by V2, V4 is covered by V5, 7 by 6, 8 by 7, 9 by 8, and so on, until I get to this one right here. Because 4k minus 2 covers 4k minus 1. 1 covers the last one, I missed the next to the last. How do I cover it? Pick one of its neighbors. I don't care whether you pick this neighbor or this neighbor. You need one of them. That means you're covering at least one vertex twice, aren't you? Okay. It's the end of the world. Who knew? Big deal. But now what happens is I have one more vertex, right? But that's odd. Common denominator 2. But isn't that what happens when you round up an odd number divided by 2? Uh, 4K plus 3 is going to give me the same idea. I'll cover V4K minus 1 with V4K minus 2. I'll need 4K plus 1 and 4K plus 2 to cover 4K plus. Oh, wait a second. I'm in the same boat. So I had to add 2 of them on. That's still, that's half, isn't it? That's 2K plus 2. Which is exactly what I get if I divide that and round up. I can just count them. All right, so what happens in the weird case? There's my cycle. So let's set up the same thing. I'll take first 2, skip 2, second 5, 6, skip 2. I get these 2, skip 2, and then I take both of these. Took this one. I gotta take that one because I skipped this one. Okay, that makes sense. I need both of these. Well, this is that many vertices. Now, I also know this number is even. Yes? And this number is exactly 1 bigger than it. N over 2 plus 2 over 2. So the only other choice I have for a domination number is 1 less than this set. I claim that doesn't work. Right? This is what we do. We rule out the smaller case to show it has to be the bigger number. So now my goal is to figure out how to make this one break. Well, that's a proof by contradiction if I ever heard one from the description. So let's assume we can do it and see what we F up. And then I'll have some minimum dominating set of this size. Okay, here comes the problem. Let's look at a string of 4 consecutive vertices. And by the way, we'll do the addition in the subscripts there, mod n, in case we wrap around the n. That's okay. So those additions are mod n. Okay. I must include at least 2 of these 4 vertices. Yes? No matter which 4 in a row I have, I must include at least 2 of those. So let's call the part of S that intersects with this SI. SI is at least 2. The only way to cover V1 is to use VI plus 1 or VI plus 2. The only way to cover VI plus 2 is to use VI plus 3 or VI plus 1. I have to use at least 2. Ideally, the 2 in the middle will cover the 2 on the outside, right? And they cover each other. So that would be a total dominating set in just this group of 4. But if this one gets covered by these 2, I still need to cover it. This one has to be covered by one of these two. The fact that those are consecutive means one of those numbers is even and one of those numbers is odd. Call those VR and VT. One of them's even, one of them's odd. I have arbitrarily decided that the R is even and T is odd. Since those are consecutive. Wait a minute. That means somewhere along the line here, there's got to be a consecutive pair, odd, even, but I didn't pick those two. Because I picked the odd one before the even, and I picked the even one after the odd. Pick two in a row, I skipped two. Then those two are the two I skipped. But that means the two before and the two after need to be there. If I skipped Vj, I have to have Vj minus 1, and I have to have Vj minus 2 to cover Vj minus 1. If I skipped Vj plus 1, I have to have Vj plus 2. I have to have plus 3 to cover Vj plus 2. Wait a second. For every I, Si is at least 2. Wait a minute. I left out a step. Left out a step. I can't write that sentence yet. I'm going to take these vertices and these two, that set of 6. I'm going to set them aside. S prime is all the vertices minus Vj minus 2, Vj minus 1, Vj, J plus 1, plus 2, and plus 3. If I take out all 6 of those, and I know that leaves 4k plus 2, total number of vertices, minus the 6 I just took out. That's 4 times the quantity k minus 1. But I have to have 2 for each Si, don't I? And out of this set, I need to have 4. Wait a minute. S must be at least 2k minus 1 plus 4. That's 2k plus 2. That's bigger than 2k plus 1, which is n over 2. Crap. the minimum dominating set has to be bigger than n over 2, and we started by saying it was equal to n over 2. There's my contradiction. That took a while to get to, didn't it? But it's just, and I say that with all sincerity, just, it's a modular arithmetic argument. Can I add mod 4 and keep track of all the things I've used and haven't used? And then it was even and odd. Oh, I like that. Those are basic ideas. I should be able to do those. This was not an obvious proof at all. The end result is really interesting. Because now I can actually give you a question. That's the oddball case. That's 4k plus 2. Let's write a dominating set, a total dominating set. Here's C10. I want n plus 2 over 2. What's n plus 2 over 2? 6. I want 6 vertices to dominate the rest. Where's my set of 6? Hallway echoes, gentlemen. Let's run with the pattern that we're coming up with. Pick 2, skip 2, right? So I don't care where you start, but if I pick 2, then I skip 2 and pick 2, right? Well, now, what have I dominated? This is taken care of, 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 and there are exactly 2 left. And they will dominate each other, and they will double count the ones around them. Every total domination set must contain at least 2 vertices. You have to contain 1 vertex to dominate everything else. You need to take 1 to dominate the one you just used. You have to have at least 2. At the worst, you use everything, right? And I can go back to my regular domination number. The dominating number is less than or equal to the total domination number is less than or equal to twice the domination number. Hey, wait a minute. I knew from our first example that the dominating number was 3. Means my total domination number had to be between 3 and 6. Turned out to be 4, but it had to be between 3 and 6. There are examples in the text Figure 1310 shows that these are sharp boundaries. In a double star, the domination number is 2. By the way, I've drawn stars of size 4. 2 stars which are connected by their central vertices. Why is the domination number of that graph 2? Technically, that's also a total dominating set, isn't it? Presto. The lower edge is as low as I can go. If I use what is referred to as a comb, take paths of length 3, and then connect all of one edge. There, that's a comb. Call the top row the U row, the middle row the V row, and the bottom row the W row. The V row is a dominating set. Yes? But that's just the middle row, which means if I want a totally dominating set, I need to hit the top and one of the bottoms, right, to cover those W's, which means I would need the entire top row or the entire bottom row to cover all of the V's. That means that the total domination number is 2n. I can go a little further, and I can make one other claim. My total domination number is less than or equal to 2/3 of the vertices in the graph. Hey, that's exactly true in this case, isn't it? I use 2/3 of the vertices, 2 of the rows. There's a lot of ideas of how can I cover, what does it mean to cover? In terms of computer networks, this is a vital idea. And in network architecture, this comes back to bite us in the ass a lot. And in visualizations of data sets, data analysis, this is a big deal. Finding a dominating set or a total dominating set allows me to isolate nodes and trends within my data. Love to tell you it's useless. I'm never going to use it again. I'm going to use this all over the place. Because I am now done with the work out of our current textbook, I have posted to our Canvas page 2 additional chapters from another book, a gentleman by the name of Balakrishnan. Chapters 4 and 5 are in our Canvas page. That's where we're going to start when we come back from Thanksgiving. Have a wonderful holiday. I will see you all then.